Okay, in this example, we'll use Kirchhoffs current law to solve a circuit and find the voltages and currents around the circuit. So let's start off with a simple circuit. I'm not going to draw a battery full circuit symbol just for clarity. We'll keep just one cell, but say it's 10 volts. We'll say that's R1. That could be R2. We'll have a second voltage in just to make it interesting. And we will connect that to that. And we will have a third resistor here, R3. Now, if we consider current flows here, the way I always look at this is if the voltage appears to be pushing the current clockwise, let's say that's true. It might not be. If it turns out that we're wrong, all that will happen is we'll get a negative answer for that current. This one, the 20 volt supply, is going to be pushing current anti-clockwise because that voltage appears to be pushing the current anti-clockwise. And when the two currents meet at this node here, there's only one way they can really go, and that's downwards. So we'll call that I3. Okay, so now let's label up our EMFs. We'll say that this one's E1, this one's E2. The voltage across this resistor, remember, it will oppose the current, so this will be V1. And this will be V3. And this will be V2. Okay, so when you first get an example or any sort of problem to do involving these, always set this up and draw all your voltages and current directions on the page. Next thing we do is write Kirchhoffs current law, KCL. So what we've got is, if we're looking at this node here, we'll say that I1 is flowing into that node, so that's going to be positive. I2 is also flowing into that node, so that's positive. I3 is not flowing into the node, it's flowing out of the node, so we say that's negative. And that's going to equal 0. So that's Kirchhoffs current law. We can rearrange that as we did before and say that I1 plus I2 must equal I3. Now, at this point, if we can find this voltage here, we'll call it Vx, we'll be able to solve this circuit, because if we know what that voltage is, then this voltage minus that voltage will be the volt drop across this resistor. And as long as we know the value of this resistor, we'll be able to work out that current. Let's put some values in. It's getting a bit busy, but let's change the colour just so we can see a bit better. We'll say that this one is a 10 ohm resistor. We'll say that R2 is a 6 ohm. And we'll say that R3 is an 8 ohm. Okay, so that's given us our resistor values. Let's change it back to black. Okay, so let's use Ohm's law now. So if we think about Ohm's law, V equals IR, or any combination of that. So if we want to represent the current I, that equals V over R. So I1 therefore must equal V1 divided by R1. So we have to decide what is V1. Well, V1 is the difference in potential between this point and this point. We don't know this voltage, but we do know what this one is. If we assume this point here is 0, then this must be 10 volts. So V1 is actually 10 minus Vx. So we'll write that. So that's 10 minus Vx. And it's divided by R1. And R1 is 10 ohms. So the current can be represented by I1 equals the voltage across the resistor divided by the resistance, 10 minus Vx over 10. In the same way, we can do the same for I2. So I2 would be, well, we've got 20 volts here. We've got Vx volts there, so current's going this way, so we're saying 20 minus Vx divided by 6 must equal I2. So I'll go straight to that and say 20 minus Vx divided by 6 is the current I2. I3 is even easier really. I3 is equal to Vx minus 0 over 8. We don't really have to write the minus 0, but just for completeness, the voltage across the 8 ohm resistor is Vx at this side and 0 at this side. So now we can substitute these values of I1, I2 and I3 into our current law equations which we've written down here. It's a good idea to label these equations you're going to use with a number like that. And then when you actually come to use them, you can say from 1 and then write your equation. And I1 was 10 minus Vx divided by 10. I2 was 20 minus Vx divided by 6. And I3 is equal to Vx divided by 8. We don't have to include the 0, because obviously it doesn't really make any difference. The interesting thing here is we've got one equation here, we only have one unknown, so we can now solve it. What I'll do is I'll pause it there and we'll do part 2 in another video.